Right on. Okay, so kind of just some options I want to throw out for you. The most obvious one, and obviously the lazy person in me is like, hey, we can just cancel it. You guys, maybe your time is better spent focusing on some other courses. No need to hold a discussion that week. We could do that. We can also just kind of try to do some kind of miscellaneous data science related topics. So, I mentioned like if there are some specific things maybe the professor covers in lecture and you want to go over it a bit more, we can do that. Maybe we can kind of walk through some data science projects. We could do that. And then there's just like special miscellaneous topics. And this was actually what the class voted for last winter. Which was a career advice talk. And I guess a little bit of background on this, as most of you probably know already, I'm not your most traditional TA from that perspective. Actually, I'm just kind of curious. Does anybody know how old I am? And does anyone want to guess how old I am? So I do have the emotional maturity of an 18-year-old. So that's probably fair. Okay, so I'm getting a lot of things here. Man, bro, Tien's saying I'm 40. That's rough, man. I know I haven't slept well, but 40? Darn. That's harsh. Okay, well, long story short, yeah, so I'm, yes, 21, thank you. Still getting carded at bars. It is kind of sad. You will go through that age where people just stop carding you at bars and you're like, really? I'm not that old. But yeah, it's going to happen to all of you at some point. But yeah, so actually I'm 33 for what it's worth. But so I graduated college. I did a master's in health policy for what it's worth. And I've been working for over a decade now as a systems engineer for a federal IT consulting company, as a government consulting company. And then I went back to grad school when I at 30 for computer science. But I guess kind of the point is I have been and I still am sort of active in industry. I still work full time in addition to everything we're doing here. So that's kind of given me like a little bit of, I guess, a little bit of a exposure to sort of, career jobs maybe that then you don't really get. And to be frank, UCLA career consulting is just atrocious. It's kind of it's abominable, the amount of just not support at all that they give you. So I'd thrown out the idea of doing like a career advice talk, things about like how to network better, how to kind of do a better job nailing your interviews, landing jobs, things like that. So we ended up doing that. I actually still have the slides up on the website right now if you want to kind of check that out. But we could do that. Other topics I'm just going to throw out. There aren't a whole lot of things I feel comfortable enough talking at you guys about for like an hour or so, but I do have degrees in economics and philosophy as well for my undergrad. Yeah, undergrad, I was like solidly North Campus. So if you ever want to get your German nihilist conversations on, we could do that. Healthcare policy. So I do have a master's in that. My work is basically just implementing federal IT sort of policy programs and technologies. So, if you ever wanted to rock on about that. And then, yeah, randomly enough, my wife is a filmmaker. And so I've sort of gotten some experience screenwriting. So, I mean, if you ever wanted to prod that thing, I will say it's my one claim to fame in the department. I'm an otherwise very mediocre computer scientist. There is definitely no Turing Award in my future, but I do think I'm the only one in the department that has an IMDb page. So that's like my one big claim to fame. So, I mean, let me know what's of interest to you guys. Again, it's your time. This is your course. So, you don't have to kind of give me a definitive up or down now, but I do want to throw that out there because we do have that kind of block of time that we can kind of be a little more open-ended in terms of the stuff we talk about. So, oh, did somebody find it already? Oh, that's funny. Yeah, so again, let me know what you want to do with that, and we will definitely go from there. Okay, project 2 already. That's kind of what I wanted to focus on today. So I don't know, just out of curiosity, has anybody actually started looking at project 2? Have you guys downloaded it, poked around with it? Anybody kind of done anything with it? Or did you take one look at the deadline, see February, your eyes just glazed over and like, I'll deal with that later. I've not found the link on CCLA. Okay. Okay, cool. So we got our work cut out for us with this. So again, it's going to be a little bit long. So good news, bad news. Good news is you're really, really going to essentially be reusing basically a lot of the code that you did last time. And particularly the code that we used for our little avocado working example where we did the classification exercise. I'm going to borrow a heck of a lot of that. So we're not really going to be looking at you to do sort of a lot of new and innovative stuff. I mean, this is basically all just going to be Python in a Jupyter notebook with pandas, NumPy, matplotlib, scikit-learn. I mean, you basically, that's it. What's going to change is going to be the specific models we use, the specific metrics you're going to use. Those are going to change. And then we're going to ask you some more conceptual questions. So, in lecture, the professor, I think, has covered all the learning models that you're going to cover with that. So you're going to do KNN, but you're going to do KNN this time as a classification exercise. Then you're going to do logistic regression and SVM regression, SVM classifiers as sort of linear decision boundary models. And then you're just going to run a naive Bayes. So I think those are going to be the models you're going to run for that. And I think we've covered all of those in lectures. The other kind of big, I guess, difference between sort of project 1 and this one is that this one we really, really want you to start thinking about your outcomes. And so, a lot of you have, I think I already have a slide on this. Do I? Oh, okay. Yeah, here. So, before we were just like saying there was that whole bake your first cake thing, just throw the ingredients together. We don't care. You're getting an RMSE in the thousands, and that's clearly terrible, but we're fine with it. We just want you to kind of do the work. Well, now we're actually going to start caring about your outputs. Now, the goal of this exercise is actually to try and, it's structured. We're still walking you through the process, but we do kind of want to start looking at the outputs of our models. We want to start looking at those outcomes, and we want to start working to kind of maximize the results that we're getting. And so these are pretty much the steps that we're going to have you take for project 2. We've spent a lot of time talking about scaling your data and how important that is, but a demonstration is worth 1,000 words on that. And so to kind of start off, I basically just have you plug in the raw unrefined data frame and then sort of run a KNN on that. And then I have you pipeline your data. Specifically, I ask you to scale it and then run that exact same model. So you basically haven't done anything beyond just simply pipelining your data and then just kind of looking at how dramatically your performance improves. It's the same data, but just simply kind of going through that steps, it'll show you hopefully show you just kind of how powerful that processing step can be. And then we're going to introduce the idea of sort of parameter tweaking. So, when you run the model, there's sort of the basic defaults for your model. Like for the linear regression, we just had you run the linear regression. We didn't have you start kind of working with all the different options and parameters you could do. So we want to kind of introduce that concept. And we're going to start you off by doing pretty much exactly what you did in the homework, right? So with the homework with the KNN, you played with the different K values. So how many nearest neighbors are you going to sort of build your model around? And it's not always obvious what the optimal sort of number is. I mean, you could probably say that a K of 1 is probably not going to be great in terms of overfitting. And then a K of 200 is probably also not particularly great in terms of like predictive power. But there's somewhere within there that's that kind of sweet thing where it's generalizable enough that you're going to get some really good outputs, but not too generalized, not too specific that you're overfitting. And so we kind of have you try to sort of tweak your KNN parameters and then sort of maximize that. And then we sort of run through some of the other models. So again, the logistic classifier, your SVMs, your naive Bayes models. And for those, we also kind of ask you to sort of tweak some of the parameters. So we do kind of a lot of interesting things using different solver models, using different error terms, using different sort of the number, we tweak sort of whether or not sort of the model is allowed to converge fully or not. And just to kind of give you a feel for how these things kind of do that. The other sort of big thing with this is we're much more focused this time on metrics. And in fact, we're going to spend the bulk of this discussion today talking about metrics for classification. So how do we think about whether or not a model is performing well? What are the different ways of sort of assessing that, and what are the trade-offs with them? And then finally, and again, this was also kind of discussed in lecture, we're going to want to do the cross-validation of our model. So anyone remember, I know professors spent a lot of time sort of digging through that, but anybody kind of really briefly can talk about like what a cross-validation is and why it's important for our model? To prevent overfitting. Okay, good. So that's one definite use of it. Kind of more generally, it's the idea that we know that the data that we have is sort of a subset of the total universe of data out there. And statistically speaking, the probability that the data we have is a representative sample, it's already kind of problematic. But then within that, we're also sort of doing that train test split. So we're randomly sort of carving our data into a training set and a testing set. And that also sort of opens the possibility that we're introducing errors into our data, that we're not errors, but we're introducing sort of biases into our data. And so we do kind of want to sort of try to kind of do a sanity check and say, okay, well, to what degree is the performance of this model specific to the training and testing data that we happen to have carved out for it, or to what extent is it going to generalize to that universe of data? And cross-validation is essentially the idea of saying, well, rather than developing the model once on sort of one carve out of the data, we're going to develop the model sort of multiple times in parallel using different sort of segments of the data. So maybe in model 1, we do train and test here. Model 2 is going to be train here with a little test and a little test here. Train 3 is maybe just here and your test data is here, something like that. But the idea being that you sort of generalize across all those models and you see whether or not the performance is kind of consistently high across that. And again, while that doesn't fully address how well it's going to perform against the broader universe of data, at least it sort of gives you some sense on the robustness of it. And then the final thing is qualitative questions. So I think in project 1, there were a number of really great questions that would come through on like Piazza or during office hours about like, why are we doing this? Like, is this important? Starting to think about kind of the different choices you have and the different options that you have. And so we want to sort of begin probing that with you guys a little bit more here. And so, there will be more qualitative questions on this, sort of, I guess, thinking questions, if you will, as part of the project. So that's project 2 in a nutshell. Yeah, I think we've kind of covered this. Is just a basic slide on classification, and and sort of, I know the professor had sort of kind of taken pains to sort of emphasize the difference between sort of a prediction model where you're going to sort of predict on sort of a continuous on a continuum basis, to classification where you're trying to sort of assign sort of a discrete limited number of categorical labels to your data. And essentially that's what a classification exercise is. And a lot of what you do in machine learning will be classification type stuff. So in fact, like what we're doing in project 2 is going to be sort of disease detection. Like, is this, does this patient suffer from a heart condition or not, right? It's sort of in this case, it's a binary classification. You can also have a multitude of classifications where you can have, like, rather than, sick or healthy, you can have choose from any number of half a dozen animals or whatnot. So you can also sort of do a multi-class classifier as well. That's project 2 in a nutshell. So I guess any questions in terms of like the scope for project 2 before we sort of try to dive into some of the content you're going to be covering. Okay, so you're feeling good with it so far. Awesome. So the first thing that we kind of want to review is balancing in your data set. And this is something that the professor had sort of mentioned in lecture, I know, but I do kind of want to spend some time on it because we are talking about this a little bit. But there is very oftentimes you are going to deal with sort of an imbalance in terms of your labels for your data set. And a classic example of this I want to give is fraud. So let's say you're working for a credit card company. Let's say you're working for Visa, and you want to build a predictive model to detect fraudulent transactions. And does anybody have any kind of notion on what percentage of total transaction volume on like a network like Visa is fraudulent? %. Almost nil, 0.01. Okay. So I remember reading, I have to kind of look it up. I think it's something on the order of like 0.3. I don't know. I should have looked this up before lecture, but I think it's something on the order of that. So, but like significantly less than 1% of your transactions are fraud. And so that sort of creates a problem when you're trying to build classifiers. Because if 99.975% of your data is perfectly valid, you're the best model, at least as judged by accuracy. And we're going to get into these specific metrics. So this is actually kind of important. If I just have a model that says, hey, I'm just going to predict this as being not fraudulent, well, then I'm going to have a model that's 99.9% accurate. I'm going to be like, okay, I'm done. I can get to go home. But that's obviously not particularly good. I'm not actually doing anything useful in terms of classification. So generally speaking, it's important that your data kind of be more balanced in terms of your labels. Now, I'm going to sort of put a big asterisk on that. And I want to sort of circle back to that. But like I have this one example here. I think I pulled this off a Stack Overflow question. Guy's building a binary classifier and he has a 2 classes. One has with a 60-to-1 ratio. And then guess what? Unsurprisingly, the logistic regression is just completely ignoring one of the labels and just essentially uniformly labeling for the other one. So that's kind of a problem. And so we do kind of need to think about balance in our data set. We do kind of need to think about that. There are no hard and fast rules to sort of whether or not your labels are perfectly balanced. Generally, a 4-to-1 ratio is considered sort of anything greater than a 4-to-1 ratio is considered unbalanced. But again, there isn't sort of a hard and fast rule to that. So I guess kind of the first question is going to be, how do we handle that in case we do have a data set that's significantly unbalanced? And there's multiple strategies. I kind of have a few options here. The first is just downsampling. If you have a very large data set, you can just simply sort of cherry pick. You can cherry pick a subset of that where you have sort of a greater relative proportion of your minority class, such that you kind of deal with your overbalancing. The second thing, is our infamous augmentations. So remember how we said we can augment columns, but we also said we can augment rows. We can sort of create new data, and so that's indeed what we can do. We can sort of create synthetic data samples. We can kind of use. There's sort of a number of techniques out there, and we've actually employed some of those with bootstrapping to try and kind of flesh out our data with sort of a representative set of samples with that. And then another thing that's kind of cool that you can do with your loss function is weight balancing. And we're going to look at some of the things we can do with that on our metrics too. But another thing just to kind of note is that you can kind of weigh the relative error of your classes a little bit differently, such that if you make an error on your minority class, you may sort of treat that disproportionately badly. So there's kind of a way of tweaking your loss function as well to sort of prioritize that. Now, I am going to mention this here because, going back to that whole like there's going to be some routines. You could almost make a drinking game out of like all these things I kind of mentioned every lecture. And one of these things is like the Goldilocks of data science, right? This like not too warm, not too cold, just right. So with balancing the data set, you also kind of have a little bit of this Goldilocks thing in play as well, because you don't always want to go 50-50 with your labels either. And can anybody think about why you might not want to do like a perfectly balanced set of labels? While I strategically eat my lunch. And you guys can just stare at me eating my lunch. Okay, good. So I'm seeing some really good. So Monik and Dan, you're both, I think, kind of getting into sort of similar ways of kind of getting into the thing. If you tilt your data, if you distort your data set too strongly, it will not be representative of the real world, right? If you build a model that will expect to see fraud 50% of the time, and you throw it out into the real world where fraud is less than 0.1%, that's not going to be good, right? And so, yes, you want there to be sufficient number of labels such that your classifier will actually do the work of classifying. It will actually learn it. But at the same time, you don't want to distort your data set enough that it kind of builds this model that over predicts a label that really shouldn't be predicted that often. And so, yeah, that will kind of throw up massive issues with accuracy when you're doing that. So again, going back to the whole Goldilocks thing, right? There's never kind of a right answer to this. There's never a, oh yes, your labels must be 50-50. There's always just a, okay, generally speaking, you need to make sure you have a sufficient number of representation. You don't want too much skew in terms of your labeling, but again, you don't necessarily want to overcorrect for that either. So yeah, just kind of things to be aware in terms of balancing your data set. So up until now too, taking a deep breath, kind of talking about this, we have been talking strictly speaking about accuracy. And we're going to break down precisely what we mean by accuracy. But at a general rule, accuracy is just simply the number of predictions you make and what percentage of those predictions are correct, right? But as I mentioned, there are other ways of measuring success. And this is particularly true for classification. And that we may sort of value certain types of errors above others. And that's something I kind of want us to start thinking about here, which is the type of errors. So there are sort of two examples here, type 1 and type 2 errors. Type 1 errors obviously are a false positive. And so here we've got this like great example. The doctor's talking to the dude and being like, hey, you're pregnant. That is a false positive. You are assigning a positive label where there shouldn't be. Type 2 error is the inverse of that. It's a false negative, where you are not assigning a label where you should have been. And so then obviously we got the very obviously pregnant woman getting told by the doctor that she is not pregnant. So we are not particularly great about that. And so just kind of thinking about why we may bias towards one or the other. And I give some examples here, but generally speaking, can you guys think about like what might be some examples where we might be very sensitive to a type 1 error, a false positive error? Can you guys think about any kind of real world examples of where maybe a false positive would be really, really bad and we want to do? Okay, good. So yeah, so Jody's talking about criminal profiling. Why would criminal profiling maybe be an example of where a false positive is really, really detrimental?
I mean, if you misidentify a potential criminal and they're just a regular person, that's not very great.
Awesome, right? Particularly for like crime, where we sort of generally our standard of evidence. So in criminal matters, and I think you're taking like procedural law courses or anything, but there's different burdens of proof. And for so there's for civil matters, there's usually what's known as the preponderance of evidence, which just says it's more likely than not. For for criminal matters, we have a status that says, actually, let me pause. Does anybody know what the level of evidence required for a criminal prosecution is?
Beyond a reasonable doubt.
Awesome. Yes, that's exactly right. For a criminal prosecution, it's beyond a reasonable doubt. Yes, exactly. So it's it's not just that it is more likely than not that the person did this. It has to be, the prosecutors have a responsibility to prove beyond a reasonable doubt that the person is guilty. So for criminal sort of prosecution, reasonable suspicion for the police. Are you talking about like warrants and whatnot? Monica, is that what you're asking? Yeah, so for warrants, oh, that's a whole other can of worms as to like whether or not police are able to sort of search without warrants and yeah, but reasonable suspicion, I think for obtaining a warrant, reasonable suspicion is the standard. You don't need beyond reasonable doubt for a warrant. But so that's a really great example of that, right? Where you, so the example I gave like is by facial recognition technology. So, for there, because we hold such a high standard for, because the fear of misprosecuting somebody is so real, and it's sort of baked into our judicial system, right? The whole standard of proof is innocent until proven guilty. So you start from the baseline of saying that this person is innocent, and then it's up to the government to prove their guilt. So because of that, we're very sensitive to false positive errors there. And so if you're building, let's say you're building a model to do facial recognition by the police. Well, then if you're looking at that, simple accuracy is important, but in terms of the type of errors you make, it's much more important for you. Yeah, it's not great if you're failing to label somebody where you should have, but it's much more important that you don't mislabel somebody. It's much more important that you don't take an innocent person and say, hey, this person is guilty. So, and in fact, in an example like that, we would probably sacrifice the overall accuracy of our model if it meant sort of preventing those type 1 errors. So do you guys kind of see maybe intuitively that trade-off? Okay, cool. So then let's talk about the other side of it, a false negative. So again, here a false negative is I fail to assign a label where I should have. So in an example, you're not pregnant, even though you obviously are. So where might be an example where we're really worried about false negatives and we might, okay, cool. Okay, COVID testing. Yeah. So why would COVID testing be an example of a false negative? Okay, good. Any diseases. So people are saying like disease testing, medical testing. Why? Why are those good examples of false negatives? Okay, perfect. Yeah. So Jacqueline, you're exactly right. So, so there's an epidemiological concern there that says it's better for us to just, if we have some doubt as to whether or not a person is tested positive, it's better just to say that they've tested positive, tell them to quarantine, tell them to isolate, in which case they can't spread the disease. But, then sort of say, oh yeah, you're fine. Just go out about and do your regular business when you're potentially contagious. So that's a great example of that. Drew, yes, that's another sort of great point, right? For a lot of these things, like if you get sort of a preliminary positive, 90% of the time, the doctor's response will be, hey, let's take you for some follow-up testing. So, if let's say, so a classic example of this is for like a lot of cancer screenings. So, they'll do sort of a preliminary test. Maybe the test will come back, sort of, they'll say, hey, there's a troubling result. Let's do a biopsy. Let's do sort of a detailed imaging scan. Let's kind of try to get down on it. So there, it's okay to say, you know what, it's okay if subsequently we determine that it's not cancer or it's not malignant or whatever, but the last thing we want to do is have the patient walk out of the hospital saying, oh, you're fine, nothing's wrong with you, if there potentially is. So there's a great example of precisely where a type 2 error is something we're really, really concerned about. Like for these preliminary tests, like it's fine if we make an incorrect initial diagnosis. It's fine if we flag somebody as being potentially, again, let's use the cancer example. It's fine if we say, hey, there's something troubling here. It may be benign, but we want to follow up on it rather than just saying, oh yeah, you're fine. So those are kind of good examples of where a simple look at the accuracy of your model maybe isn't sufficient enough for it. But let's kind of dive into some of the details about this. So I mentioned accuracy and I kind of did a little hand waving. Let's formalize what it means to be accurate. So this is a really great, I found this visual online last year and I just think it's like perfect for visualizing this. So if you think, so these two columns here are essentially so this column here on the left, these are all your actual positives. Everything on the left is a positive. Everything on the right is a negative. And then the circle in the middle is your prediction, is what you are predicting as positive. So in terms of how you read this, so essentially, this little half circle here, this is your true positives. It actually is positive, and I've predicted it's positive. This thing here is your false positives. Here I've said, oh yes, this is positive and it's not positive. It should have been negative. And then conversely, all this area here is my false negatives. These are things that actually are positive, but my prediction has missed them. So these are known as false negatives. And then lastly, I have my true negatives. So these things actually are negative and I have not labeled them as positive. So I've actually sort of correctly said that these are negative. So are you guys kind of following how this chart works? Because this is important, because as we go through our various metrics of like precision, recall, we're going to use this a lot. So I do kind of want to make sure you guys are all feeling comfortable in terms of how this puts things together. So again, your circle is your prediction. This is everything that you are saying is positive. And your two columns are what is actually positive and what is actually negative. Okay, so you guys feeling that? Okay, so accuracy. Accuracy is essentially all of your correct predictions divided by the total number, the total universe of data. So in this case, our correct predictions are our true positives and our true negatives. Those are the things we got absolutely correctly. And then our total number is just everything else. So accuracy, true positives plus true negatives divided by true positives and true negatives and false positives and false negatives. So that's accuracy.
No news, but like also just on submitted without number 4 too. I can't do it. I'm like halfway through 3. I'm still working on it, but I just don't want to do 4 anymore. Like I know for sure.
Matthew, I assume that wasn't directed
like
at us.
I pulled up the GitHub and I saw how long it was and I was just like, no, I'm not doing it.
Okay. But sounds like you're working through it, man. So moving on, next one is precision. So precision that goes back to our sort of our false positives. So it's the idea of the total number of predictions that I make, how many of those are correct. So going back to if this is our little bubble here, if this is our total number of predictions, I want to look at what proportion of those are accurate. So again, just kind of visualizing it, the total number of correct predictions divided by the total number of predictions. So it's how precise my predictor is. And again, that sort of really focuses back to the false positives. So every time I've identified a criminal, I've flagged someone and said, hey, this guy's a criminal. What percentage of those times is that person actually a criminal? So that's precision. Recall. Recall deals with those type 2 errors. So it says in the universe of things that I should have labeled as positive, what percentage of those am I actually labeling as positive? So again, looking here, of my actual predictions divided by the total universe of true data here. So it's my true predictions divided by my true positives plus false negatives. Again, just going back here, my true positive divided by true positive plus false negative. And again, deals with my type 2 errors. So basically, how many things should I have caught as being positive, but I have failed to do so by looking at this? So you guys all tracking accuracy, precision, recall? Okay, the fourth one is what's known as an F1 score, which has nothing to do with Formula One racing. It's just called an F1. Denominator for recall, yes. Okay, so again, so recall just in plain language, with recall, you want to say like out of the total universe of positives, what percentage of those positives am I capturing? So looking at this here, so again, remember going back to this thing, this first column here is the total number of positives in the universe. And then this little sort of circle is the subset of positives that I've predicted. And so essentially what recall is it says, what's the percentage that the proportion that I am predicting versus the total number of positives out there. So that's essentially, so, and again, it's your number of true positives divided by true positives plus false negatives. So those are things that we have labeled as being negative, but they shouldn't because they should have been positive. Okay, so that's accuracy, precision, recall. Yeah, so good question. So yes, so for all of these metrics, you do want to be as close to 1 as possible. Yes. A good score is something close to 1. A bad score is something close to 0, right? Ideally, just kind of talking these through. Accuracy, you want basically as many true positives and true negatives as possible. You want as few false negatives and false positives. So ideally, the numerator and the denominator should essentially be equal. Same thing with precision. You want your model to be, of all the predictions that it's made, you want as few of them to be negative as possible. So you want that ratio to get close to 1. And same thing here. You want your predictor to be as close to sort of exhaustive as possible, such that your false negative term essentially goes to 0. So yeah, you kind of want all of these scores to go to 1. So there's kind of a fourth way, which is a sort of a balanced look at precision and recall. And we're going to kind of dive in a little bit more of this, but the idea being that says, well, I'm not particularly fond of either type 1 or type 2 errors. But I want to take kind of a balanced approach of those. I don't, I'm not really fond of making either of those errors. So let me sort of take a balance of those two. And that's essentially what you're doing with an F1 score. And so the formula of it is just you're multiplying your precision and recall by 2 and then dividing it by the sum of your precision and recall scores. And that gives you that balanced score of them. And so there's an obvious question of why an F1, if you care about the type of error that you're making, if you care about the balance of the two errors, why not just use accuracy? And so we're going to get into that. Do I have that? Yeah, okay, so I have that. I'm going to go into like why you would use one versus the other, but it is a little bit different, and there are some major drawbacks to using accuracy, which is why a lot of people actually will sort of use an F1 score to sort of say, on balance, are you sort of not really making huge errors on either side? Confusion matrix. So one of the things I hope that you've kind of already gotten a sense of in terms of like working through project 1 and whatnot is how useful visualizing your data can be in terms of kind of, it's one thing to get an output. It's one thing to sort of get a chart, but it can be incredibly useful to actually visualize the type of errors that you're getting. And that's essentially precisely what a confusion matrix does. It sort of it plots out. So in this case, so this is a binary classifier. And in this case, we're looking at cancer. So malignant versus benign tumors. And your x-axis is going to be your predicted label. Your y-axis is going to be your true label. So in this grid here is where you've predicted malignant and it actually is malignant. This axis here is you have predicted malignant and it is benign. So pop quiz. I have predicted malignant, but it is actually benign. What kind of error is that?
False positive?
Yes, exactly. False positive. It's a type 1 error. So that's something precision is going to be really careful about. Okay, then bottom, we're going to start here. Bottom thing, did not predict, in this case, you're sort of predicting malignancy. So I did not predict malignancy, and indeed it is not malignant. So that's good. And then up here, I did not predict that it was malignant, and in actuality, it is malignant. And by process of elimination, what error is that? We have 2 errors, and we've already said this one's a type 1 error. So false negative, yes, awesome. And then just to kind of visualize these, so if I asked you, what is the accuracy of this model? What would the answer be? Let's see, can somebody kind of just pop quiz? Can somebody answer that? And let me do the calculation on my own. Okay, 49 88. Okay, anybody? What is the accuracy of this model? So, and remember, if you guys need a prompt, accuracy in this case, A equals true positive plus true negative divided by the universe of data. So TP plus TN plus FP plus FN. Yes, perfect. 95.8%. Okay, perfect. That actually seems really good. What about precision? What is the precision of this model? So do you guys need the formula? So again, precision is the number of true positives divided by true positive plus false positive. So it's essentially the number of predictions that you are making. So your predicted label here, malignant, divided by the number. Perfect. Yes. Again, TN for the win. 96.1%. Exactly. Okay. Final thing here, recall. What is the recall of this model? Okay, so again, recall is the number of correct predictions I make divided by the total number of correct predictions I should have made. In this case, the true label is malignant. So we're going to look at this row. We're going to divide, yep, 49 divided by 53, exactly. So 92%, roughly. And so obviously, generally speaking, that's kind of a nice, easy way to do it. But as you can see, kind of this is sort of a nice intuitive way of looking down, not at just the sort of performance of the model, but kind of breaks down where you're making errors, what kind of errors you're making, how it's distributed. So it's just like a really nice way of kind of just visualizing the kinds of problems you're getting with your data. So I want to talk about ROC curves. And just out of curiosity, I know the professor covered these in lecture. How many of you feel like you have a basic understanding of an ROC curve? Is F-score only valid? I believe it is because I've only ever seen it. So there's a question in the chat about whether or not an F-score is valid for only for classification models. I've never seen it being used for predictors because, you know, when we're dealing with predictions, fundamentally it's sort of a different. We don't deal with that kind of binary correct or incorrect thing. It's really about like the relative magnitude of the error. And so when you think about like those metrics, you know, we don't necessarily have that kind of binary prediction thing, right? Because and another way of thinking about it is with a classification, the decision is, am I assigning a label or am I not? Whereas with a just sort of a regular prediction, I am always going to make a prediction. It's just a question of how close that prediction is to the actual, you know, my Y prediction versus my Y actual. So yeah, so I've never seen an F score applied for non-classification purposes. But yeah, okay. So back to ROC curves. So I know that was discussed in lecture. Is that something you guys are sort of relatively comfortable with? Is that something we can kind of like glaze over, or is that something you want us to do it like a deep dive on? No, nobody. Okay, I'm just going to assume then that maybe we can do a little bit more work on ROC curves, just because I know it took me a while to kind of understand what an ROC curve is and why it does it. So taking kind of a big step back for a classification model, generally speaking, sort of every classification model will do sort of two things. The first is like we talk about machine learning. And so there's that learning step, which I think we're as a class sort of beginning to kind of scratch out a bit of an understanding of what it means for a learning model to learn data, but we're still not there yet. And I think we're going to get there, but we're not there yet. But generally speaking, right, we sort of first do something to our data. We apply some kind of transformation, manipulation, something to the data, to our features to kind of better sort of understand it, right? There's some kind of thing that we do to sort of understand an underlying pattern to our data. And then we apply a decision function to decide how to classify that. And so remember, like with the SVMs, we spent a lot of time talking about like the margins and those decision boundaries and everything. So there's that idea that, you know, yes, we try to kind of divide up our data set, and then there's kind of that decision boundary, and which sort of determines how we classify the data. And so, you know, so in terms of how you think about the performance of your model, we obviously just kind of mentioned those four metrics: accuracy, precision, recall, F1 score. So those are, you know, easy way to sort of think about how it performs against the testing training, you know, cohorts. And obviously you're going to want to cross-validate it. But is there a way to kind of get a sense for how well your data is parsed such that we can see kind of how well it'll perform globally? And the short answer is yes. And we can do this by sort of looking at how well our model has kind of sliced our data, right? So if you think about like that linear decision boundary with an SVM, where, you know, we've sort of figured out sort of a dividing plane between our two sort of labels. And then it's the question of kind of like, okay, how cleanly is our data set divided? And we do that, we sort of do that by changing the sensitivity of our thresholds and our decision boundary thresholds. And it's not fully clear to you yet. Hopefully in a few minutes that will make more sense, but we're not quite there yet. But essentially what you want to see is you want to see something where it's like it's carved out so cleanly that even with a very low decision threshold, even when you're allowing essentially a lot of things through, you're still sort of cleanly cutting your data. So let's first talk about like what an ROC curve measures. And now hopefully we have sort of a good frame of reference to understand an ROC curve. So remember, here's our beautiful two-columned, this is the universe of positives, universe of negatives, and here is our prediction model. So ROC curve kind of looks at the ratio between my true positive rate, i.e. my recall, against my false positive rate. And it looks at kind of the ratio of those. And we're going to show you how that sort of looks from a graph. But just to remember, recall, that's something we've already talked about. It's my true positives divided by my true positives and negatives. My false positive rate is my false positives divided by false positives plus true negatives. So essentially you're looking at like this area here divided by this area, and then this area here divided by the accumulation of this area here. And so essentially what we're looking at when we plot out an ROC curve is we're looking at the rate of true positives to false positives at different classification thresholds. And what that means is, so remember, there is, so like, and I think with logistic regressions, I think this was most explicit. Your decision function will assign a probability to a classification, right? It's not necessarily an obvious binary choice. There is a probability associated with a label, with a labeling decision. And so your decision boundary is where is your cutoff? Where are you comfortable sort of classifying your label? So a very strict threshold will say only if I have a greater than 95% confidence interval will I assign the label, or only better than a 90% or 80% threshold will I be comfortable assigning that label. That's a very strict decision classification threshold, right? That says I'm only going to assign this label if I'm really, really sure that this is correct. And again, going back to like our error types, if you're really worried about false positives, you are going to set a very high decision threshold. You're going to say, essentially, I need to be as statistically certain about this label assignment as I can be before I'm going to make that assignment. A lower decision threshold, let's say like I'm getting near 50%. So now it's more likely than not that this is correct, but I definitely don't have a lot of confidence in that. That's obviously much less likely to be the case. And then, maybe I'll even go below 50%. Maybe I'll say, as long as there is a decent chance that this label could be correct, let's say a 40% chance or even a 30% chance, I'm still going to label it positively, because as long as there's a significant enough chance, I'm not going to risk mislabeling that. So again, that's that whole cancer diagnosis thing, right? If there's a 30% chance that this is cancer, I'm going to label this as cancer and then do a follow-up test. So that's your decision threshold. So again, you have built your model, and your model essentially assigns probabilities to whether or not a label is what it is. And then my decision threshold is essentially where do I, somewhere along the lines I have to make that cut. Somewhere along the lines I have to put some of these in my positives and some of these in my negatives. Somewhere along the line I have to do that. And my decision threshold just says where along that probability curve I do it. Are you guys kind of following that? Stop me if you're not, if any of that's not really tracking. Okay, cool. So go through a short example. Yes. So Dan, let me, I want to try to visualize this, because I think that might help you do it. And the next slide sort of provides a nice visualization. And then if it's still not being clear, we'll work through another example. But I think visualizing it is going to help. So let's look at kind of what an ROC curve is telling us. So by the way, generally speaking, and this is something that we sort of looked at in class, a perfect ROC curve is this thing right in the top right corner. It essentially looks like a complete square. It's perfect. A really good ROC curve is something that looks like this. It's got sort of a nice elliptical thing. And generally speaking, for an ROC curve, you look at the area under the curve as sort of an indication. So like here, a perfect ROC score would be a 1, because the area under the curve is equal to 1. This is almost perfect. So it's not quite 1, but it's still there. This is an AUC of 0.7. And then lastly, if it's like complete randomness, then the area would be 0.5. This is what a completely random thing looks like. And then if for some reason your ROC curve is somehow like doing even worse than random, like it's misclassifying to a greater percent, your thing would look like this. But I can't even imagine you would get to that scenario, because that's, at that point you have just obviously messed up. So what is happening with this ratio here? So there is a third dimension here that we're not seeing, and that's your decision thresholds. So, and this says, as my decision threshold lowers, what is the ratio of true positives that I sort of admit into my model versus the ratio of true negatives that I admit into my model? And so, so starting from here, I start with a decision threshold of 1. In other words, I need to be 100% certain that something is correct before I'm going to label it. So there, okay, I'm only allowing in true positive, true positive, true positive. Oh, true positives. And then, and then everything. So this ratio is going straight up because remember, we're looking at the relative ratio of true positives to false positives. So at this point, I've only admitted true positives in. As my decision threshold is going from 100% confidence down to, let's say, a 50% confidence, I'm only allowing true positives in. And so up until this point, like when I hit 1, it means I have admitted at this threshold, at a 50% classification threshold, I have admitted 100% of my true positives. I have completely cleanly admitted all of my positives before I've admitted even a single negative. And so then once I get below that threshold, at some point, my false positives also will eventually go to 1 because at some point I'm going to keep going lower, 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 lower. And so eventually I'm going to let in all my false positives as well. But again, because I've admitted all my true positives before I've admitted any of my false positives, that's like a perfect 90 degree angle square. This one, it starts to get a little messy. So again, here we're starting at a 100% threshold. This is a 50% threshold. So here it starts out pretty good. We're only allowing in true positives. So that's good. Everything's good. But around here, something starts to happen. As I lower my threshold, yes, I'm still allowing in more true positives, but I'm starting to allow in more false positives too, which is why you're seeing this is not hugging the true positive ratio wall anymore, because as we're admitting more true positives, we're also beginning to admit some false positives. Now, at this point, we're still admitting far more true positives than false positives. So my slope is still sort of very much sort of arcing up instead of out, but we're sort of beginning to admit more people. And then at some point we hit that inflection point. And here we're still admitting more true positives, but we're starting to admit more false positives. And that's going to be roughly around this point here, where for every additional true positive we're getting, we're starting to get more and more and more false positives until eventually we're just admitting false positives. And now finally, this is pure chaos. Essentially, in this case, my classifier is doing nothing. It is basically no better than statistical randomness. And it says every point that I am sort of, when I lower my decision threshold, I'm essentially admitting both in equal measure. So every time I'm making a guess, half the time I'm going to get it right, half the time I'm going to get it wrong. It doesn't kind of really matter. And that's why this is sort of leveling up in sort of a perfectly synchronized manner. Because because remember, you still have your confidence interval, so it's not sort of like immediately going either way. I'm still sort of laying these up, but I'm doing these in equal ratio because essentially my classifier is doing no effective work at doing this. So let me pause there. I sort of took a lot of time to explain that, but do you guys kind of see how that works? Any questions on that? Because I know conceptually it's a little bit tricky. But again, why this is so useful is because this goes back, because remember, a big sort of underlying question for us is how well is this model going to generalize? And this sort of helps to tell you how clean your division is between these things. So something like this tells you you have essentially you've created a division such that essentially you can kind of completely cleanly carve out your data before you allow anything false in. Okay, there's a question. So why doesn't the random line depend on the proportion of actual positives, actual negatives in data? So the reason it doesn't depend on the relative number of positive and negatives is because you're looking at the relative proportion of these two columns. So let's say your data happens to have many more negatives than positives, because you're looking at the relative number of true positives to total number of positives and the relative number of false positives to total false positives to total number of negatives. If your data set is imbalanced, that ratio corrects for that. So do you kind of see why that is? Because again, you're not looking at the total number that you're getting right. You're thinking about the ratio between them. And so that's how it kind of corrects for imbalance in your data set. But that's a really good question, because when I was talking about this, I was talking about sort of admitting different numbers, but in reality, what you're looking at is the ratios between these. And so it doesn't matter if in real life you have twice as many positives as you have negatives, because your ratio will correspond, will sort of correct for that essentially. But yeah, that's a really good question. So any other questions in terms of an ROC curve and what it's telling you and how to sort of interpret it? And so again, kind of bringing that full sort of swing back to this, it really kind of tells us how good a job we've done carving our data into two, how good a job we've done in terms of sort of assigning the relative predictions to it. So aside from like the nuances of our particular model, and aside from the sensitivities that we assign to our decision function, it tells us kind of just how cleanly our data can be chopped off. And that in turn begins to tell us to what degree this is going to generalize. Because if we get a nice sort of clean separation, if we get something that looks like this, it tells us that chances are the data that we encounter in the universe is going to sort of nicely fall into here, and we're going to be able to characterize it properly, because we can see here that we can kind of cut it very cleanly. Okay, so we got that. Okay, cool. So any more ROC questions? I think everything else that we cover in terms of metrics, I think is pretty straightforward. This is like the one thing that is a lot less intuitive and a lot more abstract. So I threw a lot of metrics at you. And again, for project 2, you're going to be asked to solve all of these. You're going to be asked to generate all of these as part of your project 2. So the question is kind of, okay, when are you going to use which one? So here's kind of, there isn't necessarily a hard and fast rule to these, but here's some sort of just general kind of guidelines, if you will, for why you would use one versus the other. So generally speaking, accuracy is used when you really care about true positives and true negatives. So those things are very important. Whereas F1 score is usually used when the type of errors become more important. And again, we sort of talk about like you would use precision and recall specifically when you care about either your false positives or false negatives. Now, another thing that is like critical, because remember early on in this discussion, we talked about your balance of your data set. So accuracy is a more useful representation when your class distribution is similar. So when you have a more balanced data set. But if you have an unbalanced data set, accuracy can be very, very misleading. And let me give you an example of that. So let's say you have a confusion matrix of, I'm just going to write this out. So again, let's say I'm going to, do I have my little whiteboard? Where's my, oh, hang on. Oh, can I just annotate directly on this? Can I do that? Oh, this is going to be so happy if I can do this. Stamp format. Okay, can I just, oh yes, okay, great. So let's say I have my little confusion matrix here and I predict. So this is, so my y-axis is going to be my predictive, my y-axis is going to be my, or my x-axis is going to be my actual. And so here I'm going to predict 98. Actually, hang on. Let me make this a little easier. Oh, wait, okay, draw. So 97, 1, 1, 1. And there's a square there and a square there. So again, confusion matrix here. So I have predicted 97 and in actuality it's 97. Here I have predicted 1 where it should have been not. So that's my false positives. Here I should have predicted this one and I didn't, and this one I predicted right. So really quickly with this, what is my accuracy in this case? So accuracy, again, is going to be my true positives and my true negatives out of 100. Okay, I'm sorry, I'm writing with a mouse pad, so that's not great. So accuracy here is my true positives, 97, and my true negatives, which is 1, divided by the total universe, which will be 100, so 98%. Now let's look at precision. So precision, in this case, would be the total number, I guess, divided by the total number that I should have. And so here, maybe I reversed these wrong. I don't know, whatever. Here it's 97 divided by 98. And then, oh, you know what? I'm sorry, guys, just to make this easier, let's reverse the labels. So let's say that this is the negative and this is the positive, because I think that'll make it, because this is not a good example of an unbalanced data set. So precision here is total number that I should, so this is my true positive, and then this is my false positive. So essentially it's 1 out of 2, which equals 50%. And recall is going to be the same thing. So recall is the universe of data should have been this bottom row. Actually, no, actual is column. So the universe should be this, but I've only predicted that. So that's also going to be 1 out of 2. So 50%. So again, so let me just stop annotating this. So again, my accuracy in this case is equal to 98%. So if I look at that, I'm going to say, oh, great, my model is great. But then if I look at my precision and recall in this case, equal 50%. That's not particularly good. And the reason that this is so skewed is because my labels are so skewed. And so particularly, so again, going back to the example earlier on, like credit card fraud, it's very easy with credit card fraud to get accuracies of nearly 100%. But when you start looking at precision recall metrics, then you start realizing, oh, actually, either I'm making a lot of false predictions relative to the total number of predictions I'm making, or of the fraudulent cases out there, I'm catching very few of them. So getting back to this sort of bullet point here, if you have sort of generally, if you have a balanced data set in terms of your labels, accuracy is a pretty good metric. But if it's unbalanced, F1 score is generally better. And I'll tell you that as a result, typically people tend to sort of bias towards an F1 score when evaluating whether or not a model is good. So that's why most of the time people use F1 scores. We had already talked about confusion matrices. Those are like super useful when diagnosing performance issues with the model. So if you're making different types of errors, if they're biasing a certain way, confusion matrix is just kind of a quick and easy way of just like visualizing how you're classifying things and what the errors are that you're making. Again, you can kind of infer that from prediction, recall, accuracy, like you can kind of predict those things, but it's just nice to throw it up and see it and just immediately visualize it. And then again, ROC curves are just a really great indication of how cleanly your data is sort of parsed and sort of how well it allow it to generalize. So Any questions on sort of the trade-offs of your different metrics and why you would use one or the other, or maybe not use one or something like that? Meantime, I'm going to erase all this. Okay. So last but not least, let's talk about how you actually encode this. So the good news is very, very easy to encode these. I didn't even include a coding library because it's just really, really easy to generate these things. You will already import your metrics library. And so within those are very basic scores that you can sort of do. So again, within the metrics, there's already sort of an accuracy score library there. Your inputs are just going to be, so in this case, target test is your actual label. Predicted is the label that you generate. So I don't know if I need to write that out, but your predicted is what your model generates as the label for your test data, whereas your target test here is your actual data. So again, I can just pull accuracy that way. I can pull precision, recall, metrics, and then I just sort of have some nice formatting here just to kind of give you sort of a nice standardized table for this. And then confusion matrix. So you're given a, so if you just do a, if you just print your confusion matrix, like you will get sort of a standard thing. It doesn't look that great. So we actually give you a helper function called draw confusion matrix that kind of allows you to format this really nicely. And again, same kind of deal. You input your predicted labels versus your actual labels for your test data. Then you can input the different columns for each. So in this case, healthy and sick. And then it'll just output a nice kind of color-coded sort of relative proximity number here. So all of those metrics that we have just talked about, literally it's a line of code each. And so for the project 2, that's all you're going to be asked to do for this. In terms of generating these. So it's really, really easy to do. Again, Python just honestly at this point just makes it so easy it almost feels like cheating. So that's for that. ROC curves, a bit more to do there, but even that is really not bad there. So I guess kind of the things to note for here are you, typically kind of the way Python sort of assigns different variable outputs is, right, you sort of set up a list in front of your equal sign, and then you sort of call your function, and then it just kind of returns those things. So in this case, you call the metrics ROC curve thing, and that generates your false positive rate, your true positive rate. In this case, this is an example for the SVM model. So, and then your relative threshold value, right? So it's a 3-dimensional array. Because remember, this is a 2-dimensional plot of TPR and FPR. But if you think about it, there's like a 3rd dimension going out into the Z-axis. That's your various threshold. So it's really looking at like a 3-dimensional plot. And then again, your target test score. Oh, that's something I should have. Do I need to specify? Hang on. Let me stop sharing for a moment. I think I may need to tell people how to get score. Sorry, guys, give me just a moment. Oh, okay. Yeah. So score, let me actually just show you with this. I'll just show you directly. I'll just test it, share it directly. So get your score, that's kind of one additional step you need to do. So this will all seem very familiar to you. So this is the example of SVM. So again, you define your model. It's going to be the support vector classifier. Then you do for your model, you're going to do the fit on your training features, your training labels, and then you're going to get the result. You're predicting labels. You're just going to apply that SVM model that you've now trained. And you're going to sort of call the prediction function to your testing features to get your predicted thing. And then the only other thing you need to know about your score is you also call this additional function here, this predict underscore probability. And so because remember, for each label, in order to get that true and that false ratio, it's about the probability associated with that. So that's why you need the probability score as well. So that's all you're calling when you run that. So where is this? Okay. So again, you have your score, and then there's just simply this sort of pie plot things. So you're going to generate your figure 1. It's going to be a plot of your false positive rates, your true positive rates, x-axis, y-axis. You can assign a color, the line width of the color. You can assign plots, x labels, y labels, and then you just do the show thing to actually generate it. But yeah, from a metrics perspective, that's essentially what you're doing. And I will tell you that between that and generating your model, that's probably 90% of the coding you're going to do on this project. So again, let me pull up the chat, make sure I haven't seen. Okay, so yeah, questions about this? I know I threw a lot at you. Okay, I have lulled you all into a state of comatose exhaustion. More generally, I need project 2 questions. So again, this is going to be due not next Tuesday, but the Tuesday after next. So February 9th, before class, 10 a.m. Pacific, upload on Gradescope. Just like project 1, you're going to output your Jupyter Notebook as a PDF. So an easy way to generate a matrix of histogram plots, one for each column of the data frame. Oh, that's a good question. So I think the easiest way to do that, honestly, and I don't have a good sort of easy pseudocode for that, but I would say probably the best thing you could do is just sort of define an array, which will be your columns, and then just do a for I in your columns, and then for each thing sort of plot the histogram of I. And then it'll kind of just loop through and plot all of them. That's generally the approach that I would take for that. I don't know if it'll turn out nicely. It'll probably just stack them one on top of the other. But that's probably the easiest way just to kind of do that in bulk. But yeah, good question. Any other project 2 questions? Okay, so if there is nothing else, I'm gonna sort of open you guys up for a, by the way, nobody sent me memes this week. I'm deeply heartbroken by that fact. But little Savannah, DJ Little Boba, she spin up a fun track for us. I'm gonna set you off there. I'm gonna kind of, anyone who wants to stick around, I'm gonna break you out into breakout groups. Maybe get you to start working on the project, start working on the homework. Address any sort of questions you guys will have. It's kind of open session time for you guys. But yeah, other than that, I'm gonna give you a DJ Shark. Oh, thank you, Dan. Oh my God. Yeah, before I forget. Yes. Okay. Who won the contest? Denise won the contest. Oh, awesome. Okay, hang on. Let me stop sharing. Denise, are you on? Can you come on cam? Take a victory lap.
Hi.
Don't want to put you on the spot if you're not cam ready, but congratulations. Can we
Thank
get
you.
a round of applause for Denise? Denise, can you DM me your email?
Yeah, sure.
Okay, awesome. And Dan, thank you for that. Okay, and by the way, there's a general question. Yes, test questions are going to be very much in the style of the homework questions, of course, without the Python coding associated with them. Yes, very much so. Okay, I'm going to stop the recording now. And then again, whoever wants to stick around, again, we're going to break you out into breakout groups, start talking about the projects, homeworks, course, life in general, just kind of give you guys some open time. So.